This will be our first lectured video for our pre-calculus class, and all of these notes can be found in Canvas, and I would recommend, if you have access to a printer, that you would print them out and keep them in a 3-ring binder, and that way as you watch the lecture videos you can follow along, and then you'd have some completed notes to use as a study aid as you do our homework and prepare for our exams. Let's begin with Chapter 1, where we're going to review function and function notation. When we talk about a function, it's important to remember that a function has 3 parts. The first part of a function is a set of input values, referred to as the domain of the function. The next part is a corresponding set of output values, which we call the range of the function. And then finally, between these two sets of input and output values, we have a rule that assigns to each input a specific, exactly one output value. So when I write the equation f of x equals 5x plus 1, what I'm talking about here is my set of input values, and we'll talk about this later, is going to be all real numbers. So I could input any number for x, and I would get a result. The corresponding output values, or the range, are also all real numbers. And the rule that assigns them is the equation 5x plus 1. Because if I start with x equal to 1, then by the rule, the output value at 1, f of 1, so this is the function value at the input value of 1, is equal to 5 times 1 plus 1. So that's going to be 5 plus 1, and we would get 6. And this shows us that for a specific input value of 1, it gets sent to the corresponding output value of 6. So that's just a quick example of one function, 5x plus 1, kind of identifying the 3 parts to the function. So the thing to keep in mind is a function is a rule that assigns for each input value exactly one output value. And we can represent a function by a graph, an equation, or a table. Let's first look at how we might express a function by a table. For our first example, we are going to determine if the relation given between the input and output value is a function, and we know it's a function if for each input or x value there is exactly one output value. So let's take a look at our first example. Here, for the input value 0, it tells us the corresponding output is -2. For the input of 1, the corresponding output is 3. For the input 2, the corresponding output is 4. And then for the input 3, the corresponding output is also 4. And let's just check whether it fits this definition. If you have a fixed input value, do we see that there is exactly one output value? And we don't want to get confused here, because we might want to say, oh well, these both have the same output value, but that would be different. That would be saying for each output value there's exactly one input value, which is kind of the reverse of what we're talking about when we discuss a function. So this is a function because every output value that you look at, or every input value, has exactly one output value. So we know 0 goes to -2, 1 goes to 3, 2 goes to 4, 3 goes to 4. But this next example, focus in on these 2 entries. Think if these 2 entries break our definition of a function. If you would take a moment and pause the video now and think about that, unpause when you're ready to discuss or hear the discussion of whether this is or is not a function. Notice we've got the same input value that at one point is sent to 3, but at another point is sent to 4, and this does not follow the idea of a function, because for a specific input value 1, it's getting sent to 2 output values. That means this is not a function. So each input can only go to one output. Often we're going to want to express functions in an efficient manner, and for that we're going to use function notation. So in function notation, we are defining the input and output variables and showing the function relationship. So if we see the expression f of x, that should be read as f is a function of x. What's in the parentheses think of that as of, so f is a function of x. And in this case, the input variable is inside the parentheses, and the output variable is outside of the parentheses. So that can help us keep things straight. So we know f is the output variable, x is the input variable. And we can use different variables as well. So if I say g of r, that's representing the function, the fact that g is a function of r. Now let's turn our attention to the next example. It says if your job pays $9 per hour, then the money m in dollars that you make depends on the number of hours h that you work. So if we're going to write a formula for the money that we earn after working h hours, we know that for each hour we work we get $9. How many hours are we working? We're working h hours, so we could write this as 9 times h. And now this next problem asks us to find the money earned for working 5 hours, and specifically use function notation as we write out this problem. So in this case we are going to let h take on the value of 5. So we would get 9 times 5 by the formula. So we earned $45. But if we want to show our answer using function notation, then what we want to make clear is the fact that we earned $45 for 5 hours of work. So we would express it as the money earned for 5 hours of work is $45. And this is expressing our answer in function notation because it tells us the output variable, the money earned for a specific input value 5, was this value. Next we're asked to find m of 10. So we would read this m parentheses 10 as m of 10, telling us the money earned for 10 hours. Explain what it means. So let's first just follow the formula. That's going to be $90. And in this case, the 10 is the input. And in our formula, the input is h in hours, so we know h is 10. So the idea is if you work 10 hours, then you will earn $90. And that's exactly what m of 10 equals 90 represents. So if you work 10 hours, you will earn $90. Now our next example is similar, and I think this is a great opportunity to pause the problem right now, read through the problem, work at step A, work at step B, and then after you finish working through that on your paper, unpause to check your work because I'll discuss it again, and this will just help give clarification on what concepts you're understanding, which ones you need more clarification on. So if you could pause now and then unpause when you're ready to check your work. So in this example, we have the height of a winning pole vault in the early years of the Olympic Games can be modeled by this formula, where t is the number of years since 1900. So here we want to be careful. T is number of years since 1900. And then h is the height of the winning pole vault in meters. So if we're first asked to calculate h of 4, this means everywhere there was an input value t in the formula, let t take on the value 4, so we would have 0.05 times 4 plus 3.3. This is going to be equal to 3.5 meters. And then if it ever says explain in practical terms, that just means explain what the variables represent. So we know the input is representing years since 1900, so t equals 4 years since, that was our t value, 1900. That corresponds to the time 1904. So we could say in 1904, the height of the winning pole vault is 3.5 meters. Next, in part B, we're asked how much does it increase from 1900 to 1904, and then 1904 to 1908. Now at this point, we might recognize that our equation is a straight line. And if we've heard this before, then we might know that straight lines have constant rates of change or constant slope. So whatever the increase from 1900 to 1904, that's going to be the exact from 1904 to 1908. But if we were not familiar with that, then another approach is to just find the value of h at 1900, at 1904, at 1908, and then properly subtract them. Now our formula does not work for the year. It works for t values where t is years since 1900. So we'd first want to say 1900 is at t equals 0, 1904 is at t equals 4, 1908 is t equals 8. And then we're going to find the outputs at these points based on our formula. We already found h of 4 before, so we know that's 3.5 meters. We don't have to calculate it again. That's from step A. Now, whenever we substitute 0 in for t, this whole term goes away, and we're just left with 3.3. So we know that's 3.3 meters. Now, if we let t equal 8, we've got 0.05 times 8 plus 3.3, and we would end up with 3.7 meters. So if we're looking at the increase from 1900 to 1904, we're just going to take the later value and subtract it from the previous value. So we'll always take the later and then subtract the previous. So we've got 3.5, the value in 1904, minus 3.3, and we've got a 0.2 meter increase from 1900 to 1904. Now from 1904 to 1908, we would take the later value at 1908, which is 3.7, subtract that from the previous, so we'd have 3.7 minus 3.5, and again, as expected, we have the same increase over the 4-year period, because since our equation is a straight line, for a fixed change in input values, we should have a fixed change in output values. Up until this point, we've discussed the general definition of a function, and we've also seen a function expressed by a table, and then recently through a formula. So now we're going to talk about a nice way that if you're given a graph, you can identify whether you're looking at a function or not. So if we're given a graph, then we can use the vertical line test, which will be abbreviated often VLT, to determine if something is a function. So for instance, for our first graph, the vertical line test is if you could fix any input value, imagine drawing a vertical line through that input value. If it never intersects the output value more than once, that means that it's a function. So for instance here, we don't see any repeats, intersections, whereas the second one, imagine if I pick this as my input value, then we see that it intersects the curve twice. Same as here. So because the vertical line intersects the graph more than one time, this is not a function. Similarly here for our ellipse, any point that I pick on the interior would pass through twice, so it's not a function. Now if we pick the very end points, it only passes through once, but it's still not a function because other values did not pass the vertical line test. And the reason the vertical line test works is it fixes an input value. So it's saying pick an input value. And then what it does is it verifies that there's only one corresponding output value. Because what you're doing when you're looking for intersections is you're looking for corresponding output values. So if for a fixed input value, your vertical line through that point only intersects the graph once, that means for this input value, there is one output value. Whereas in this example, for this input value, do we see there were two output values defined, and that's why this is not a function. So the vertical line test fixes the input value and verifies there's exactly one output value. So we've discussed what a function is. Now we're going to discuss a specific type of function, which is one-to-one functions. A function is one-to-one if for each output value, so now we're starting with the output value, we can see that there is exactly one input value. So one-to-one refers to one output for one input. Now the function f of x equals x is an example of a one-to-one function because exactly each output, any output value that we pick, for instance 5, has an output value, and there's only, for that output value, there is only one input value. So if we were going to sketch a one-to-one function, we would just want to make sure if we pick an output value that there couldn't be, for instance, this is an example of a not one-to-one function. And this is a shorthand you can use because the reason it's not a one-to-one function is if we fix this output value, do you see that it corresponds to two input values here and here? So for this one we have for a single output value two input values, so this is not one-to-one. So if we want to draw something that is one-to-one, we would want to make sure that maybe something like this would be one-to-one. For each output value that we pick, there is just one input value. Or we could also draw something like this. The idea is for a one-to-one function, we could not turn around, because once we turn around, we have for one output value multiple input values. So that would be not a one-to-one function. So anything that's just increasing or just decreasing would be a classical one-to-one function. Now, if we're given a graph, previously we saw that the vertical line test can tell us when something is a function. Similarly, in order to tell us something is a one-to-one function, we can use the horizontal line test. And with the horizontal line test, if you want, you can abbreviate this HLT. So the way the horizontal line test works is you look at the graph of your function, and you think about fixing an output value, any output value this has to work for. So let's fix maybe 1. And then you draw a horizontal line through that output value, and you see how many times it intersects the graph. Notice here it intersects the graph 1, 2, 3 times. Since it intersects the graph more than one time, that means there's more than one corresponding input value. So that would tell us that this is not a one-to-one function, because for each output there's not necessarily just one input. So for the horizontal line test, you would just think about visualizing horizontal lines through the graph and ask yourself, does it pass through the function more than once? If so, it's not one-to-one. If each horizontal line only passes through the function once, it is one-to-one. So the reason the horizontal line test works is that by picking a horizontal line to look at, we are actually fixing an output value and then verifying that there is exactly one corresponding input value. So as we were thinking of sketching an example of a one-to-one function, we realized the idea is if you start increasing and then start decreasing, that would make something not one-to-one. So we can't have that change of behavior between increasing and decreasing. So one thing that we could say about one-to-one functions is it's going to be either strictly increasing or strictly decreasing. So if we know a function is like this, then we know it is a one-to-one function. Now, whenever we go to Calculus 1, we'll be able to reframe this idea of strictly increasing and decreasing as derivatives, but this is not a part of our class. This is just kind of a foreshadowing of what would come in a future class. It's going to be helpful to have in your mind some basic examples of one-to-one functions and other characteristics. So I have a list here of some well-known functions that are not one-to-one. For instance, x squared is not one-to-one. Looking at the graph, try to visualize y. Notice it does not pass the horizontal line test. Any polynomial whose highest power is an even positive integer, and the reason for that is if you've got an even polynomial whose highest degree is even, then eventually the end behavior will look like this, or something like this, with maybe things more complicated in the middle of the function, but eventually at the end, no matter what the middle part looks like, you're going to have parts of the function not passing the horizontal line test. A function that you'll learn more about in trigonometry, sine of x and cosine of x, these are also not one-to-one, and there are others, but these would be the basic four that we would want to remember for our class. So we've talked about which functions are not one-to-one. Now let's talk about well-known functions that are one-to-one. So the cubic function is one-to-one, x cubed, because for any horizontal line that I pick, we see it intersects the graph only one time. And then any polynomial whose highest power is odd would also be a well-known one-to-one function. We have the function f of x is 1 over x is also one-to-one. 1 over x looks something like this. And the reason it's one-to-one is that, notice while we've got something that's decreasing here and decreasing again, if we picked any horizontal line, it would only pass through the graph one time. So this does pass the horizontal line test. A straight line, any straight line with non-zero slope passes the horizontal line test. The function e to the x, we'll talk about this more in a later section. It's a strictly increasing function, so it is one-to-one. Natural log of x will again come up in more detail in a future function, but it is also one-to-one. So try to just keep in mind these different categories of basic examples of one-to-one and not one-to-one functions. Now this section is in the notes, but we're not going to include it in our class, so don't worry about showing that something is one-to-one outside of using the horizontal line test. So if you have your notes printed out, you can kind of just X this out, and let's continue on to the next page. Now, this is something that I highly recommend students do, is they have in their mind an understanding of the shape of some of our basic graphs, because if you know just from looking at how a function is described how the graph looks, that's going to help you in all your future classes. So I've listed here what we might call our toolkit functions. These are some of the most recurring functions that you're going to see in our class and possibly future classes, so it's good to know what their behavior looks like over their domain. So just take some time to read through this list in your notes and familiarize yourself with this material if you're not familiar. We've got the behavior of a constant function is always at the same height. Notice that is definitely not one-to-one because it has infinitely many input values for the same output value. So we know this is not one-to-one. We know the graph f of x equals x is the straight line with slope 1 through the origin. So this is one-to-one. Here we have the graph of the absolute value of x. I'm going to take a moment. If you would pause the video and think to yourself whether the absolute value of x based on this graph is one-to-one or not. So pause and then unpause. So this function is not one-to-one because we can think about the horizontal line test and see that one output has multiple inputs. Now for our next one, we've got the quadratic function f of x equals x squared. It looks like this parabola, which we also see is not one-to-one. Here we've got our cubic function, x cubed. Looks like this. That would be one-to-one. 1 over x, we've seen this before. Has this behavior. We've got what we're going to learn in the future is a vertical asymptote at x equals 0 for 1 over x. So this one is one-to-one. 1 over x squared has this shape. What do y'all think? 1-to-1 or not 1-to-1? Pause, write down, and then unpause to check your work. This is not 1-to-1 because if we fix an output value, we see it intersects the graph more than one time. We also have the function for the square root of x. It starts at 0 and then increases from there in that pattern. And we would see this is 1-to-1. So all of these graphs, what you would want to do is just try to commit them to memory based on the function. Try to memorize what the graph would look like, and you can either do that by inputting some table of values to kind of get an understanding of why the graph behaves that way, or just by memorizing the shape of the graph. Our final one is the cubic root. So we're looking at the cubic root of x, which could also be written as x to the 1/3, and we see it has this behavior. Okay. So this comes to the end of our first lecture. I'd recommend you would check Canvas for the homework problems that I've assigned from the textbook. Complete those homework problems. Remember that they are all odd, so you can check your answer in the back of the book, and then seek help for any problems that you missed or you'd like more clarification on, either by sending me a Canvas email, stopping by virtual office hours, or going to the PSC Math Lab. And then just check Canvas for future assignments. Thank you.